Hey, welcome back to Physical Science. We just finished Module 4, and this is going to be Module 5. Today, in Module 5, or this next module we're going into, since you all have dealt with chemical equations now, there's a couple things we got to fix. We've been kind of going along violating one of the main principles of science, and that is the conservation of matter. In other words, those chemical equations we've been writing, the number of the elements on the left side of the equation and the number of elements on the right side of the equation, they actually have to equal out. So we have to do that and take care of that. That will be Module 5.2. Here in Module 5.1, what I want you to do is you've got to be able to look at a chemical equation, and you're going to start being able to see some patterns with these equations. Sometimes it looks like things are getting made, sometimes it looks like things are falling apart, some things look really complex. And we're going to go over those, and I want to show you at least the 5 categories. There's 4 main categories, but there is a 5th one I want you to pick up along the way. So this is Module 5.1, Types of Chemical Reactions. Make sure to stop the video every time you need to get caught up on your notes, but everything you're going to see on this PowerPoint today is absolutely important. Make sure you write it all down. Okay, here we go. Now, the first type is the simplest one. The first type of chemical reaction is called a synthesis. Now, synthesis comes from the word where you've probably heard of an electronic keyboard, like a synthesizer. A synthesizer's job is to mix together different kinds of sounds. You know, with the different buttons you can push on a synthesizer keyboard, you can make it sound like violins, you can make it sound like trumpets, you can make it sound like something funky if you want to. And the synthesizer will mix all that together. So synthesizing means you are bringing things together, you're adding things together. Now, if you look at this equation right here, I just wrote down A's and B's. I'm not going to use any chemical elements right now. I just want to show you a pattern, okay? Just a pattern. Make sure you write this down. So if we have element A and you've got element B and they're on the left side of the equation, they combine together. That's their arrow right there. Shows it yields or it's going to produce. And notice they've bonded together over there on the right-hand side. Now, we've already done this 40, 50 times since the last module. So, but this is actually a specific pattern. If you got 2 or more single elements over there on the left-hand side, and they want to combine with something over there on the right-hand side, then that is called synthesis. And there's the pattern I'm going to show you there with arrows. They come together and they form one thing. And here's a good example. Make sure you write down this example and how water is made. Now, if you burn hydrogen gas and you burn oxygen gas together, of course you get something very powerful, a lot of heat, big reaction out of that if you burn those. But when the exhaust or the byproduct of those after the reaction is H2O, which is just water. So you've got 2 things, 2 different kind of elements on the left-hand side. They're coming together to make one compound, a covalent bond compound on the right-hand side. Now, let's go on to the next one. It's just the complete opposite. What happens if you already have a compound on the left-hand side, like A and B together, and for whatever reason, they split apart over on the right-hand side? That's just like the leaves when they fall down from the trees in the fall time. They go down on the ground and they begin to decompose. So that's what these are going to do. They're going to go through decomposition. So we've got elements A and B on a compound on the left, and for whatever reason, on the right-hand side, after they react, they actually split apart. They decompose. There's a lot of chemicals that we have that go through decomposition. A lot of things in our refrigerator go through decomposition. And to show you there with the arrows, there you got A and B, and they're splitting apart to separate. And a good example one to make sure you write down is something you probably have in your house, hydrogen peroxide. The stuff that is in the brown bottle, to help slow that reaction down, they don't put it in a clear bottle, they put it in a brown bottle. And hydrogen peroxide looks a lot like water. It's H2, but it's O2. So there's an extra oxygen in there. And given time in that brown bottle, it naturally decomposes and splits up into just water and oxygen gas. All right, going on to the third type, chemical reaction. Remember, if I'm going too fast, stop the video. Make sure you got time to write all this stuff down. The third type gets a little more complex. This is called a single replacement. Okay, a single replacement. Where look at the compound over there. We got A and B together on the left side of the equation. You got A and B are bonded together, And then we're going to combine it in a test tube or a beaker with chemical C. Now they're going to react together, and if you look at the right-hand side, you see something switched. And if you'll notice, element B, whatever that is, it left A and it went over to B and bond with chemical C. Okay? So we've got one switcheroo, so to speak. Okay? We placed one element over onto another one. So you've got one single replacement. Sometimes they refer to it as a displacement. But either way, single replacement or displacement, you've got one single element there. B is going to leave A and goes to B with C. Okay, a good example one to write down. This looks kind of complex, but you got calcium chloride with fluorine. And then if you look at the right-hand side of the equation, whoa, calcium's no longer with the chlorine, now it's with the fluorine. And it's left chlorine all by itself over there. So calcium is the one that did the single switcheroo. It left chlorine to be with fluorine. So that is a single one replacement. Now I also want you to know something else. Notice how long the equation is getting. It's getting longer and longer and longer. And that becomes very evident when we go over this fourth type of chemical reaction. Now this fourth one, you got to really take some time to look at it, really figure out what happened. On the left-hand side, you got A and B together, and you got C and D together. On the right-hand side, well, A is no longer with B, now it's with D. So that's one switcheroo. And C used to be with D, now on the right-hand side, C is bonded with B. So that's a second switcheroo. So kind of like swapping dates on a double date there. Okay, they have swapped over. The B and the D have swapped around, both of them, so that's a double replacement. A good example, well, up first I got a little diagram here for you. But a good example equation, man, look how long that equation is. And it's got a polyatomic ion. But remember, we're going to always treat polyatomic ions like they're just one single element. Because at this stage of physical science and our level of chemistry, we're not going to take a polyatomic ion and split it up. Okay? So you've got silver, Ag, is bonded with nitrate, NO3. And then on the second part, you've got potassium, and it's bonded with chlorine. Now look at the right side of the equation. Silver is no longer with nitrate anymore. Now it's with the chlorine. So that's one switcheroo. And potassium is no longer bonded with the chlorine. It's now bonded and switched over to the nitrate, the NO3. So that's two switcheroos. That's a double replacement. Now something very important I want to make sure you put in your notes. Look how long that equation is. That's a good rule of thumb. It's kind of a cheat a little bit, but I want you to remember that if you got this big, old, long equation like that, and you're sitting there going, man, is this a single? Is it a double? Is it a synthesis? Is it decomp? I'm confused. I don't know what's going on here. Just remember, if it's really big and long and complicated looking, you can almost bet all your money on the fact that it's probably going to be a double replacement. All right, now on to the extra one. Remember, there's only 4 types of chemical reaction, but there is a 5th one I want you to learn about, and that is called combustion. Now in combustion, the key thing here is the O2. See that O2 flashing over there? That O2 on the left-hand side, any element, I just put an X in there, but any element that combines with O2, if you see an O2 on the left side of the equation, no matter what's on the right, I don't care, but if you see O2 on the left side of that equation over there, that means combustion is getting ready to occur. Okay, good example is aluminum. Easily and very quickly, in fact, actually reacts to oxygen and goes through a combustion process. Actual real pure aluminum, if you buff it and clean it and not let it be exposed to oxygen, it is as shiny as silvered mirror. It is really shiny. But most aluminum that we all see has got this frosty gray surface on the outside. That's because that if you were to polish down and take that layer of gray frosty stuff off, get down to the shiny aluminum, it instantly reacts to the oxygen in the air and becomes frosted and colored again. Okay, now we're going to go into a separate category, and this one we actually already did in a lab in class. At least the year that we're recording this, we did this already. We talked about an endo and exothermic reaction. We did a measurement, and we saw how when we mix 2 chemicals together, they got really, really hot. Okay, and in fact, in the lab, what we did is we combined magnesium metal with uh, with the acid, hydrochloric acid, and that began to bubble and everything and fizzle away. And we were also measuring the temperature, and our temperatures in our little beaker containers went up to like 103 or 107 degrees Fahrenheit. So that was definitely an exothermic. Endothermic means just the opposite. It's going to get really cold. Now let's go on through this because I want to show you the details. The part we did not go over in the lab, here are the details. Endothermic reaction, the chemical actually absorbs energy. Now another way I want you to think about that, absorbs energy, it absorbs heat from its surroundings. If you actually have a test tube in your hand and the chemicals inside there are going through an endothermic reaction, they're going to absorb the heat from your hand. The heat from your hand will actually get absorbed into that little test tube and to your brain. Anytime heat leaves your hand, that means that that object that you're holding on to is cold. So a chemical reaction that absorbs energy in its surrounding is an endothermic reaction. Here's a great example, and notice the flashing 101.7 kJ. Now what that means, this is brand new to you, so make sure you write this down. kJ is actually a unit of measurement. It's a unit of measurement for energy, okay? Energy. And yes, it could be chemical energy, it could be thermal energy, it could be all kinds of sorts of energy, but in this particular case in chemistry, we're talking about heat energy. So sometimes they'll actually write the actual number like this one, 181.7 kilojoules, or they actually might just write the word heat in that little blue box right there. But the key is this. The equation, or the heat, is on the left side of the equation. Okay, I want you to notice that. That is important that you write that down. Like I already said, I put on there, most endothermic reactions will feel cold to the touch, since it's taking heat away from your hand. But the other important thing is that the extra joules of energy is on the left side of the equation. Make sure you circle the word left. Okay, you got to memorize that. The endothermic reactions, the heat is on the left side of the equation. And then you can guess on an exothermic, which is the next one, instead of absorbing heat, it's going to give off heat. So it's going to actually feel hot to the touch. A good example is every time you fire up the grill or you burn propane, that's what C3H8 is. That is actually propane. Propane, when you light it up, it combines with O2. See that O2 right there? 5O2. Now that 5O2, remember, anything that combines with an O2 on the left-hand side, that's combustion, right? Just go back to our last little lesson there. But what comes out after you burn propane is you get carbon dioxide, that's that CO2, and you get water comes out of it. And look at that number on the end over there on the right-hand side in the red box. You get 2,220 kilojoules of energy. In other words, that's heat that comes out after the reaction. You see, we're on the right side of the equation after the arrow there. So that's heat that comes out of the reaction after the reaction. So that is an exothermic reaction. So anytime you have an exothermic reaction, if you're holding on to the test tube, that heat's going to be coming out of that test tube, which means that test tube is going to start feeling warm or pretty hot in your hand. Okay? And also, don't forget, the kilojoules, the joules of energy, are going to be on the right side of the equation. Again, circle the word right, put a star by it, memorize that. Exothermic, the numbers are on the right. And one more time, I'm going to remind you that sometimes they'll give you the numbers like 2,220 kilojoules. Sometimes the scientists really don't need to know the exact amount of energy they want. They may just write the word heat, H-E-A-T, right in that box right there. They may just throw that right into the equation, either on the left side for an endothermic or on the right side for an exothermic. But it really doesn't matter that much. We're not going to be messing around with the actual amount of energy, although that is really fun if you go study in higher levels of chemistry and physics. We really can use that energy to study things that go in farther. All right. Thank you for tuning in today.